Welcome you all to the NPTEL online certification course on smart grids, basics to advanced technologies, and today we are going to talk about virtual inertia and ancillary support. Please focus that in any power system, especially in microgrids, as you all know that the energy which are available to us is through multiple resources, and most of the time those energy resources at distribution level being locally generated, and maximum contribution could be from renewable energy resources. The challenge here, by increasing the renewable resources at low voltage network, probably reduce your system losses, and most of the power being generated at high voltage level through synchronous generators, and then generation capacity got reduced, and then need not flow to the extremely lower end, because you could generate something at low level. So, that the power which is coming from high voltage to low voltage is being reduced. So, the transmission losses become less. Now, please try to understand that because of generations are not completely produced through synchronous machines, the system inertia may reduce because of contribution that is coming from renewable generations, and especially from non-moving devices such as PV and storage generations, batteries, PV and battery storage generations. So, as you all know, the system of such a large magnitude, any variation in load is very common. Load is keep on oscillating, but those oscillations can easily be managed by my huge generators. Probably they could be from hydro, thermal or nuclear. They can easily manage those variations of load through the inertia available to me through my huge generators. And now, when the inertia is not available to me, how do you match out those variations in my load when the system inertia is partly reduced? Probably by having 5 to 10% of those non-inertial sources in the system may not affect much, but when we move towards 30 to 50% of non-movable generating sources and non-inertia systems, then it is quite challenging for the system to balance between load variations, because the system do not possess enough inertia power to manage those variations. So, it is important for us to understand how to extract inertia from those stationary objects, especially PV and battery storage systems, where power electronics devices available to me within distribution systems and partially medium voltage systems, we can extract some of the inertias which are available to us, though they are not moving devices. That is the main focus of today's lecture about virtual inertia. And then second could be the ancillary support, how those power electronic devices can help me to support the system and extend its benefit to few ancillary support system. Now, the future power system evolving paradigm over the globe, and as you could see, the left side, this is my yesterday, and the right side which is my tomorrow. So, this kind of system we had in the past, and now we are expecting the system to look like this. We had large power plants, and then we have centralized mostly national networks, and then we had actually huge power lines, and then the customers or consumers at the bottom. So, production, market, transmission, distribution and consumer. However, tomorrow what we are expecting, those huge power plants, especially the thermal power plants, will be certainly be replaced by your green energy generation power plants. So, you will have huge number of wind power plants, solar power plants, and hence the market become a decentralized market, no more one source of energy transfer. It is like a both way economics, and then you will have actually the transmission corridors, and but you will have maximum storage technology in between. So, these two things, your renewable generation and storage devices, seems to me are the new entities. These are the new entities compared to my yesterday's power system. And then certainly finally the active participation of the system means the residential systems may have again the storage. So, the storage, solar, wind generation, these units are quite common and new compared to my previous conventional power systems. Now, because of this new power system into field, now introduction of electricity generating sources into distribution network historically contain only loads, which is not true. Power electronics converters behavior fundamentally different from conventional synchronous machine, do not participate in the conventional control of the network. Power electronics equipment depends on the strength of the grid to which they are being connected to, and uncontrollable and intermittency nature is an issue. Now, because of which I think we need to see that we have made our system modern, but what are those things we have compromised, and that might have led to reduction in inertia, which is reasonably not acceptable to any system. So, how do you balance it out? Now, if you look into the renewable integration in any power system across the world. So, this is the world map as you could see. So, the color as you could see, which is varying from 5% to 100% of renewable, and I could see that excluding a few areas, okay, I think most part of the world they have accommodated renewable energy significantly. And we could see India here, where actually still we have actually approximately 20% of renewable, which is a good test. So, this is the reference, you can note it down, HANA, Max, Pablo 2020, they have given such a wonderful data. So, please refer that. Now, once you move to the global scenario, what exactly happening through the world map, and we have different regions and percentage reduction in inertia constant because of renewable penetration. Let us understand what is happening. Now, first actually you could see it is 4 to 3, the second which is Asia, which is 4 to 3.8, then you could experience United States, which is 4 to 3.75, then you have South America, which is 3.5 to 3.25, and because of which you can compare that European Union and Asia, USA and South America. Okay. So, this is my European Union, and then you have Asia, then you have actually US and then South America. There are 4 zones where you could clearly see the inertia which has been significantly dropped, reduction in inertia constant because of replacement of polluted energy resources by green energy resources, and the percentage is as high as European Union, which is 25% in reduction in inertia constant because of non-rotating installation devices. And then Asia, which is 5%, USA which is 6%, South America which is 6.5%. Though wind power they do have certain amount of inertia present to them, but it is not as high as your thermal generators or hydro generators. Now, when you look into the kinetic energy which is available to us, and especially in Indian scenario we have focused on, and you could see that the renewable energy penetration in percentage which is keep on increasing, okay. And these are the years actually 17, 18, 19, 20, 22, the colors as you could see we are very very seriously proceeding, you know. The available kinetic energy also keep on decreasing. Now, from 16, 17, 18, 19, 20, 22, you can see the kinetic energy mean, kinetic energy median, kinetic energy minimum and kinetic energy maximum. So, this is the year wise statistic of estimated kinetic energy. Now, if you try to analyze inertia analysis under high renewable energy source integration scenarios, application to the European interconnected power systems. So, we will derive to a interesting conclusion here. As you could see that these are my frequency variations, and you could see the renewable energy integration, and you can also see the renewable energy integration, and you can also see the ROCOF with respect to variation in the load in percentage. So, now it is very significant the way it was and the way it is now moving towards. So, the frequency because of renewable energy sources integration, you could see that the percentage when it is going to be 5, 15, 30, 45 and 60, as you could see that how the inertia values or inertia constants are keep on reducing in a given system. Now, when you talk about frequency support which is an essential reliability support, that is ERS, which is very important, you have to maintain your frequency of the system constant all the time. So, here across the world if you focus the frequency which is the maximum which is 60 hertz in northern Americans, and rest of the systems are close to 50 hertz. So, frequency represents an indication of the real time balance between supply and demand. Declining frequency indicates more demand than supply, while rising frequency indicates more supply than demand. Frequency balance must be maintained within tens of millihertz of the target 60 hertz, or it could be 50 hertz. So, this is how actually we run the system, and this is my load, and this is my generation, and then we get some frequency support. When the frequency is not as desired, then we have to get some frequency support, and this essential reliability support in functional terms can be defined as frequency support ensures the frequency of system is stable for both normal and contingency conditions. Controlling frequency can be broken into 4 stages. First is inertial response, and then we move to primary frequency response, then secondary frequency response and tertiary frequency response. So, these are the 4 stages. Now, daily operation of system requires a continuous balance of load and resources, and operational flexibility is needed to manage real time changes in load and generation. So, every time the variation between load and generation or the difference will lead to a frequency change, and that need to be balanced through essential reliability support mechanism. Now, effect of lack of ERS availability, if you do not have mechanism to meet out your frequency support, so what are the consequences? Large frequency deviation can result in equipment damage, okay, which is not good, and perhaps we all are expected to have 50 hertz means 50 hertz, and probably a small variation, but if you operate with 49.2, then I think it is not a good power system to me. So, large frequency deviation can result in equipment damage and power system collapses. interconnection frequency deviation can result in loss of generation, load shedding and interconnection islanding. So, when you experience frequency variation, frequency support is not available to you. So, in the position where you are not having lot of essential reliability support ERS, then probably you may lose lot of generations and load shedding may be one of the option to you, and put system stability and reliability at huge risk. So, which is not good. Imbalance in generation and load can overload transmission facilities. Protection equipment can malfunction or be damaged. Prolonged imbalance can result in violation of NERC reliability standard, which is BL 011. So, I think you need to have essential reliability support, that is ERS, especially for frequency in power system, which is mandatory. Now, the same ERS, there are a couple of important definitions that we need to understand. Now, the ERS element, let us focus on what is inertia to me, and that by definition it is a stored rotating energy in a machine. I have already described in the beginning of my lecture today. It is accumulation of inherent response of conventional synchronous generators, that is CSG, that arrest frequency decline. So, probably because of the inertial energy which is available to me, which will not allow my frequency to vary because of the both capacity of observe and release as and when needed. Now, there are different type of service for inertia provided inherently by synchronous machines, may be provided through deliberate control of renewable energy sources, local frequency sensing applicable to virtual inertia only, and the response time T in order of cycles. And let us now move into primary frequency control mechanism. In case of primary frequency control ERS element, which is an important component, automatic and autonomous response to frequency variations through a generator's droop parameter and governor response. And what kind of services those primary frequency control provides? They provide local frequency sensing provided through generator governor control and can be provided through deliberate control of electronically coupled wind, solar, storage and other distributed resources. No communication infrastructure required and also may include automatic load shedding. Now, T in order of seconds. Now, when you move to secondary frequency control, one of the important element of ERS, this is a service that returns frequency to normal and minimizes unscheduled transient power flow due to power imbalance between neighboring control areas. Now, let us say you have a system which has prior commitment to cater power through two different tie lines, but when you have serious problems probably through secondary frequency control, you will control your frequency and also minimize the unscheduled transient power flow due to power imbalance between neighboring control areas. So, because if there is a tie line, you will be affected through the variation that is happening in the area number 2, or due to the problem in area number 1, the area number 2 will be experiencing certain challenges. So, centralized within control centers through AGC is a significant communication infrastructure typically provided by generation, but some distributed resources can provide these services also. It is a quite slower than primary frequency response, and this is in order of 15 minutes. Okay. So, first one is few cycles and then second is few seconds and third which is a few minutes. Now, virtual inertia and ancillary support, what and why? Why do you need ancillary support, number 1, and what do you understand by virtual inertia. Now, in order to counterbalance the decrease in inertia, virtual inertia is utilized. Means when the system inertia is reduced due to some reason, now we have to explore the availability of virtual inertia, and that can be utilized to compensate the reduction in inertia in the system. Now, virtual inertia is realized by implementing the control function on the power electronic interfaced renewable energy sources to mimic the conventional generators inertial dynamics and provide the inertia virtually. Very, very important, I am repeating it again. Virtual inertia is realized by implementing the control function on the power electronics interfaced renewable energy sources, very important, to mimic the conventional generators inertial dynamics and provide the inertia virtually. So, that is my virtual inertia. The main source of virtual inertia is the short term stored energy in the DC link of the distribution system of the renewable energy sources power converter, which should be injected to the AC side according to the virtual inertia control objectives. I repeat again, the main source of the virtual inertia is the short term stored energy in the DC link of the renewable energy sources power converters, which should be injected to the AC side according to the virtual inertia control objectives. And you could see the basic energy conversion. So, this is my conventional system with synchronous generator, and the same thing mimicked through my power system with power electronic devices. Now, if you focus on sources of virtual inertia and ancillary support, now generation types and capability of the grid stability. Now, we have different sources, for an example conventional synchronous generators, DFIG wind turbine generators, PMSG wind turbine generators, PV array, battery storage and demand response. Now, it is important for me to understand out of those generation types, how many of them actually provide inertia and how many of them provide active power control. You will be very, very happy to know, excluding the PV array, all of them actually provide both inertia and active power control. In case of PV array, probably there is no inertia available to me and they provide only active power control. Now, those inertias available to me from the wind generation and demand response, they are not the perfect inertia. So, they are the synthetic inertia response possible with deloading and corresponding control mechanisms. So, the perfectly available inertia is from conventional synchronous generator and the battery energy storage. PV array cannot provide inertia and rest of them are having a mixed opinion. Now, virtual inertia from renewable energy sources, application to the European interconnected power systems, and we could see that this is my frequency and the time. You could see the way the frequency drops and rises, and probably you can also plot the characteristics for delta P load, which is keep on increasing, and delta PL is my variation. And finally, the very important part is that in case of European interconnected system, it has been seen that the virtual inertia requirements are significantly high, because they do experience, as I have shown in the past, yes, as you could see, there is a reduction of 25% of inertial constant. So, probably they are it is important for them to have lot of virtual support. So, virtual inertia, these are coming from renewable energy sources in European interconnected power system is significantly high compared to other networks. Now, when you talk about virtual inertia and demand response, we can experience similar kind of structures. So, there are few case studies for thermal power plants, biogas power plant, solar photovoltaic and wind turbine. Okay. So, these are the characteristics which can easily tell you the kind of power output and experienced at different levels. So, this is again thermal, bio, solar and wind turbines, and you can see that because of demand response mechanism. So, how a virtual inertia can be generated through demand response programs, and it is very important for us to know when you have two multiple areas, let us say, and based on the behavior of two different areas, the virtual inertia of area number 1 and 2 can be controlled to an extent. Now, there are bit of challenges when you go for limitations of renewable energy and demand response for frequency support application. The main problem with renewable energy are possibility of no power generation from renewable energy sources during a frequency event and intermittent nature of renewable energy sources, which is quite uneconomical to operate in deloading mode, and limitation with demand response is quite significant. Complexity involved in sophisticated communication and control mechanism required for demand side contribution. For an example, you see when you talk about demand response activities, okay, here what is happening that when the load and source there is a mismatch, and through demand response programs actually probably the gap can be reduced and you can certainly create some virtual inertia out of it. But the biggest challenge is that you do not know how the customers will behave, because if you curtail certain loads or if you allow some discomfort, they may not be happy about it. So, demand response programs, until unless there is an agreement with the consumers that you can allow some significant portion of your loads to be controllable, and I can control at any given point of time as and when I need inertia. So, probably it is a quite complex approach through demand response, but certainly it is an option that can be explored in modern urban customers, but not to all. Apart from the above mentioned point, the total amount of provided flexibility does not entirely compensate for the substituted CSG. Also, 4 major ancillary support can be provided simultaneously by renewable energy sources and demand response. Now, virtual inertia and ancillary support from your virtual synchronous generator VSG. I think this is a very important concept. It is basically a non-rotational device, but which act like a synchronous generator in a pseudo form, and hence it is known as virtual synchronous generator VSG. So, VSGs are a control application for enabling converters and inverters based technologies to mimic the behavior of traditional synchronous machines, including reciprocating diesel generators, gas turbines and synchronous condensers. Now, virtual synchronous generator VSGs provide many of the same grid stabilization services as traditional generators, including system strength, system inertia, frequency regulation as well as voltage support, and are unique in their ability to be tuned via software adjustments. You can see the basic diagram for your virtual synchronous generator VSG, all right. So, you could see this is DC bus, diesel generator, DC-DC converter, PV arrays, power grid
and this shows the converter which can be used to mimic the synchronous generator characteristics and is popularly known as VSG.
Now, when you talk about virtual inertia and ancillary support from the VSG, similar to the prior renewable energy sources as well as demand response. Now, it is very interesting to see that you can see there is an inertia, frequency control, system strength and voltage control. So, probably the technology mapping for 4 major ancillary services that stabilize my electric grid, and this one of the very important part is my synchronous generators, and then you can also see the battery energy systems are the 2 important parts. So, whenever it is needed we can use or engage your storage technology and its conversion mechanism to the grid can be used for virtual inertia support. Now, I will be happy to say some of the research work that has been carried out by the research scholars at IIT Roorkee Admire Lab. Case study virtual inertia from BSG with BESS and increased integration of renewable energy sources in islanded IITR distribution system. What we have assumed, so this is the IIT Roorkee campus network, or I can say for some extent distribution network too, and these all blue patches are nothing but my PV panels, and then we have a huge diesel generator 4.5 MVA considered, and we have assumed a VSG of 1.5 MVA, and you have a battery of 200 kilowatt hour as you could see, and we are proposing the battery in 4 different sites excluding which has already been physically deployed in the campus in the Department of Electrical Engineering. So, we are proposing there could be a 100 kilowatt hour battery, 150, 150 and 200 approx. So, approximately 200, 500, 600, 800 kilowatt hours of storage integrated to the system and 2.8 megawatt of PV in 35 different locations of the campus with a diesel generator and virtual synchronous generator in place. So, assuming all this infrastructure, we have carried out bit of virtual inertia analysis of the system, and first actually we carried out analysis with RSCAT for IITR distribution system. This is what the runtime window look like, and we have obtained certain simulation results, though we do not expect actually a scenario of islanding that may occur in the system, but for as a research initiative few scholars have attempted to understand this campus is having huge amount of renewables, and we do have synchronous generators in the campus, diesel generators, and probably a small scale analysis for a virtual inertia can be carried out. So, what we have seen in the case number A, where increment of power reference of the VSG by 100 kilowatt, and case B increment in load by 30 kilowatt to 70 kilowatt. Okay. So, by doing this what you have realized what is the small inertia which is 50.12, large inertia which is 50.1 and the bang which is 50.08. However, in the case B the small inertia which is 49.88 and the large is 49.9 and the bang is close to 49.88. Then the question comes actually how to quantify the inertia, which is a very important task. So, during first few seconds of power imbalance, considering initial variation of system frequency and a known size of disturbance which is delta p, relation between inertia of system E system and initial ROCUF can be given by this equation, and then considering a diesel generator probably E system which can be defined in the equation number 2, and the E DG output being initial output of the DG can be obtained by measuring delta P DG. So, ROCU of a terminal of the generator, K1, K2 can be obtained after measurement at terminal of the both DG and VSG, and after that, after mathematical modeling and PHL validation has been carried out, and inertia provision for decrease in PV output at Big Kunz a specific location, and inertia provision of increase in PV output at earthquake engineering department. So, we have determined what is AC current, BSS current, PV current as well as frequency. So, that gives a clarity how the virtual inertia provision available to us through a PHL validation being carried out. So, to importantly to conclude that virtual inertia and ancillary services and support schemes are quite important for modern power systems, and we have seen today different kind of analysis that we have carried out after understanding a special case study of IIT Roorkee distribution system campus network has been demonstrated. These are the references we have used significantly, and you can refer those, and probably this is one most of the materials that we have used from the 6th one. And thank you very much for your attention and patient listening. Thank you very much.